In the last video, I talked about the idea of standard error. I said that a standard error is a standard deviation of a sampling distribution. I said that if the possible samples in a sampling distribution are clustered close together, then the standard error is low, and if the possible samples in a sampling distribution are highly spread out, then the standard error is high. I also said that if the standard error is low, then the selected sample is likely to be more accurate because the selected sample is less likely to be an extreme outcome way out here or way out here. Also, if the standard error is high, then the selected sample is likely to be less accurate because the selected sample is more likely to be an extreme outcome way out here or way out here. In this video, I wanted to go into more detail about the standard error. First, I wanted to go over the formula that's used to calculate the standard error. The formula that's used to calculate the standard error depends on what statistic is being calculated with the sample. The two most common statistics that are calculated with a sample are a sample mean and a sample proportion. A sample mean is just an average of a sample. If a person records the heights of a sample and then calculates the average of those heights, the answer would be a sample mean. A sample proportion is really just a percentage of something within a sample. That's because a proportion is just a percentage written as a decimal. For example, if a group of people is 75% male, then the proportion of males in that sample is 0.75. If I ask the members of my sample about their genders, and then it turns out that my sample is 75% male, then my sample proportion is 0.75 for males. When a person calculates a sample mean, or a sample average, the person is trying to estimate the population mean. For example, a person who calculates the mean height of a sample is trying to estimate the mean height of the entire population. And when a person calculates a sample proportion, the person is trying to estimate the population proportion. For example, a person who calculates the proportion of males in a sample is trying to estimate the proportion of males across the entire population. The person is trying to find out what proportion of the population is male. When a person calculates a sample mean to estimate a population mean, or a sample proportion to estimate a population proportion, the outcome isn't guaranteed to be accurate. In other words, the sample mean isn't guaranteed to be close to the population mean, and the sample proportion isn't guaranteed to be close to the population proportion. There could always be some sampling error. Remember, we learned that sampling error is the amount that a sample statistic is off target from what it's estimating. So if the sample mean is 10 away from the population mean, then the sampling error is 10. Or if the sample proportion is 0.25 away from the population proportion, then the sampling error is 0.25. Sampling error is just the amount that a sample statistic is off target from what it's estimating. Whenever you calculate a sample statistic to estimate something about a population, you don't know exactly how much sampling error you're making because you don't know what the population statistic equals. You only know what your sample statistic equals. However, if you take a random sample and calculate a sample statistic like a sample mean or a sample proportion, it's possible to calculate a value that tells you how much sampling error you should expect to occur, or how much sampling error is likely to occur. And that value is the standard error. The standard error tells you how far off target a certain random sample is likely to be from the population statistic that it's estimating. The word standard means typical, and error means off target. So standard error is the amount that a random sample is likely to be off target, or the amount that a sample statistic would typically be off target in a certain situation. So if a random sample is being selected, and the standard error turns out to be 10, then the sample statistic is likely to be about 10 off target from the population statistic. It's not definitely 10 off target, but that's what it's expected to be. A standard error tells you how much sampling error is expected to occur. If the standard error is low, then not very much sampling error is expected. An accurate outcome is expected. If the standard error is large, then a large amount of error is expected. The sample is expected to be not very accurate. The symbol for standard error is either sigma and then an x bar, or sigma and then something called p hat. I'll explain why. X bar is a symbol for sample mean. So this symbol for standard error is the standard deviation of the sample means in the sampling distribution. Right here, it's the standard deviation of the sample proportions in the sampling distribution. P is population proportion, and p hat is sample proportion, and n is sample size. So we've covered the formulas to calculate standard error for sample mean or sample proportion. Let's go through a few examples of calculating a standard error. Here's our first example. A person wants to estimate the mean age of a city's population. The standard deviation of this population is 12.7. That's the amount of dispersion in the ages in the city. The person dials 200 random phone numbers within the city, asks each of the 200 people for his or her age, and calculates the mean age of the sample. The person adds the 200 ages and divides by 200 to get a sample mean. And this is saying, what does the standard error equal in this situation? To get the standard error, you take the population standard deviation, which in this case is 12.7, and divide it by the square root of the size of the sample that's being selected. In this case, the sample size is 200, so we divide 12.7 by the square root of 200. You can do this in a two-step process. First, on a calculator, just put 200 under a square root sign and get the number. The square root of 200 is 14.14. After you do that, just divide the fraction. 12.7 divided by 14.14 is 0.9, and that's the standard error. I rounded it to 1 decimal place. This says, how far is the sample mean expected to be from the population mean? In other words, when this person calculates the sample mean, how far is it expected? How far should we expect it to be from the mean of the entire city? Well, since the standard error is 0.9, it's expected to be 0.9 from the population mean. We're expecting the sampling error to be 0.9. Now that's not definitely what the sampling error will be, but that's what's expected in this situation. Here's another example. In this example, a person is calculating a sample proportion to estimate a population proportion. In a certain population, 45% of the people are planning to vote. So the population proportion is 0.45. And a certain person doesn't know that it's 0.45, and that person wants to estimate what this population proportion equals using data from a sample. The person dials 250 random phone numbers to get a sample of 250. The person asks each person in the sample if he or she is planning to vote, and then calculates the proportion of the sample it's planning to vote. In other words, the person calculates the proportion of people that are planning to vote within the 250. So if, let's say, 50 of the 250, if 50 people out of 250 are planning to vote, then the sample proportion would be 1/5 or 0.2. So the person is calculating a sample proportion with data from a sample to estimate an unknown population proportion. This says, what does the standard error equal? To get the standard error for a proportion, you take the population proportion, which we know is 0.45, and plug it in for P, right here and right here. You take the sample size, which is 250, and plug it in here for N. Then first you subtract in parentheses 1 minus RP is 0.55. Then you multiply on the top of the fraction. 0.45 times 0.55 is 0.25. Then you divide this top number by the sample size of 250. 0.25 divided by 250 is 0.0001. I left it to 3 decimal places. And then the square root of this, if you press the square root key, is 0.03. That's our standard error. And that standard error is telling us that the sample proportion, or the proportion of the sample that's planning to vote, is likely to be 0.3 away from the population proportion of 0.45. In other words, the sample proportion is likely to be about 0.3 this way or 0.3 out this way. It's likely to be some number between 0.42 and 0.48 because we're expecting a sampling error of roughly 0.03. The standard error is telling us that in this situation that's being described, the typical amount of error that's expected is 0.03. That's typical for this situation, which is why this is the standard error. The standard error is just the typical or standard amount of error that's expected in the situation you're dealing with. Now let's talk about the factors that affect the standard error. Well, first let's mention that the standard error is the amount of sampling error that's expected to occur in a situation, but not the amount that will definitely occur. For example, if the standard error is 0.52, the sample statistic should be about 0.52 off target, but that's not what it'll definitely be. It could be more off target or less off target, just depending on chance. Also, when the standard error comes out to a larger number, a larger amount of sampling error is expected. In other words, if the standard error is larger, the sample statistic is likely to be further from the population statistic. The standard error goes up when either the sample size is smaller or the population has more dispersion, because these two factors both contribute to more error in a sample. When the sample size is small, the data in the sample, when the sample size is small, the sample statistic, like the sample mean, will be more affected by extreme values in the sample, which means that you would expect the sample mean to be more off target. Also, if the population has more dispersion and the population members are less similar to each other, then you're more likely to get extreme values in the sample that'll throw off the sample mean. If the population members have low dispersion and they're all very similar, then you're less likely to get an extreme outcome. Then you're less likely to get an extreme value in the sample that'll throw off the sample mean. So here's one quick example of this point. If I the error will also depend on the bias that went into the non-random sampling, and that bias isn't predictable.